we're going to talk about improper integrals. And the idea of an improper integral kind of deals with some of the requirements of what our functions need to be in order to have a well-defined integral. So some of those things mean that, like, if you take the definite integral, you need that function to be continuous on your interval, right? So if we have a definite integral, so a definite integral, for example, a to b, the integral from a to b of f of x dx, so it requires f of x to be continuous on the interval a comma b. Okay. Furthermore, the interval a comma b must be finite. Okay, so you need to have like a clear beginning and a clear end. Now, improper integrals they throw everything about this away. So improper integrals allow you to sort of fiddle around with this in such a way that all of a sudden you don't need your function to be continuous on your interval, and you can also have an interval that's infinite in length. Okay. So there's different types of improper integrals that kind of have to do with which rule we're breaking. I think a lot of people sort of break it down into type 1 and type 2. That's how your textbook does it. That's how most other textbooks break it down. So let's talk about type 1 and type 2 indefinite or improper integrals. So type 1. That is when you have this type of situation. So an infinite interval. Okay, so type 1 deals with an infinite interval. So we basically have 3 situations that you can have. So you could have the integral that goes from a to positive infinity of f of x dx. And the way we deal with this is that we just set this equal to a limit. Okay? So this is actually going to be equal to the integral from a to c. Oh, sorry, that's not quite it. We say that this is the limit as c approaches positive infinity of the integral from a to c of f of x dx. So the way we get around this is just by setting it equal to a limit, okay? And you can probably imagine where the other ones are going to go. So another one is where we would have negative infinity to b f of x dx. And this is equal to the limit as c approaches negative infinity of the integral that goes from c to b of f of x dx. And finally, you can probably guess where this next one is going to be. So this is where we have the interval that goes from negative infinity to positive infinity of f of x dx. Okay. Now this one, the way we get around this is we just split this up into 2 separate integrals. So this one is going to be the limit as, let's call it, what does the book say? Yeah, let's actually get limits out of it. So let's say that this is equal to the integral from negative infinity to a of f of x dx. We already have that as a definition. You could use any letter that you want, because we're going to use a over here. So basically we cut it off at a, and then we pick it up at a for the next interval. So basically what we're doing here is, the first situation is where you have some kind of integral that kind of goes off, and obviously it would have to get smaller and smaller and smaller in order for it to converge. So that would look something like this. So this is what this first one would look like. So this would be the point A, and we would just take the limit as c goes to infinity. The second situation is going to look something like this, okay, where we have some kind of function that is kind of going off in this direction, and this is the point B over here. So this is the point B, and we're going off to negative infinity. Now the third situation, what we have to do is we have to sort of split it up. Okay, so our function is going to look something like this, and it's going to go off in both directions. And we're calculating the area under that curve. And at some point, we kind of have to split it up. So that can be any real number A. And it doesn't matter which number, because the greater the number, the bigger this integral would be, and the smaller the integral, the greater this integral would be. So it doesn't matter which value you choose, as long as you choose the same value for both integrals. Okay, so you just split it up in half, and then you've got two indefinite integrals. Okay?
And then would you think, okay,
Yeah.
yeah.
Okay, so just to be clear, these go off in both directions. Okay? Now, if the limit does exist, we say the integral converges. Otherwise, it diverges. Okay? So we have, so in other words, i.e., we can have convergent or divergent improper integrals. Okay, so we've seen situations where a limit doesn't exist. If that limit doesn't exist, then that means that we have if the limit doesn't exist, then we just call that integral divergent. Okay, so that's the type 1. Let's talk about type 2 integrals, okay? Or type 2 improper integrals. Okay, so type 2 deals with a discontinuity in the interval, okay? And there's, again, 3 possibilities for this. So the whole idea of this is dealing with the fact that, maybe our functions are not continuous on the entire interval, but we can still take the integral. We just have to do so with a limit, okay? So let's talk about how this works. Okay, so one case is, so if f of x is, let's see, continuous on, let's say, a comma b, like this, but discontinuous at b, we have the following. Well, the integral of f of x from a to b is equal to, well, you can probably guess where we're going. The limit as, let's use the variable t, as t goes to b, of the integral from a to t of f of x dx. So again, we're just kind of replacing everything with a limit. So This is assuming that f of x is continuous everywhere on the interval except that endpoint. Well, we can just take the limit and see where that goes. And we'll do some examples and see what this looks like in a minute. Similarly, I could probably even skip this one because it's just kind of the mirror image, but I'll write it down anyways. So if f of x is continuous on a, b, but not including the point A, but discontinuous at A, we have, you can probably guess it, that the integral from A to B of f of x, oh, I forgot my dx over here. dx. Dx, that's equal to, well, the limit as t approaches A from t to b of f of x dx. And I forgot about something. So we're actually taking a one-sided limit here, because it's possible that the limit doesn't, the limits are different from one side to another. So this is actually, this first one, I have to make a little amendment here. This first one, this is taking the limit from the left, and the second one is taking the limit from the right, which I hope makes sense, because that's the side of the interval that we're on, right? So it's going to be helpful to draw some pictures here. So this first one here, this could look something like this. Okay, so this might look like maybe we've got some kind of function that's doing something like this, and then all of a sudden we have like an asymptote at a certain point. Okay, and then this would be, so this would be A, and this would be the point B. So you can see that we could just take the limit and see where the limit takes us. And remember that we're taking the limit from the left in this first one, and in the second one we're taking the right-handed limit. So it's going to look something like this. So kind of a mirror image, like that. Okay, and then on this side here we would have the point A. So it's discontinuous at A, like you can kind of imagine it shooting off to infinity at the point A, but then it's fine everywhere else. So in which case we would just take the limit, in this case, as t approaches b from the left, and in the second case, we would take the limit as t approaches a from the right. And finally, the last case is, again, kind of like the last case in the type 1. So if f of x is continuous on A to B, including both of the endpoints, but discontinuous at some C, with A being less than C being less than B, we get that the integral from A to B of f of x dx is equal to the integral from A to C of f of x dx plus the integral from C to B of f of x dx. Okay, so keeping in mind that this second case is just, or this third case is just the first two cases kind of done at the same time. So keep in mind that this C here, we're still undefined at C. So this is kind of like the first type. So I guess we could call this like type 2A, and this is kind of like type 2B, right? If we were to call these A, B, and C.
So you'd have to take a limit.
Exactly. So this would be, so this, so i.e. we have two limits. to take. Okay? So, I mean, the long and short of this is just that you can include limits in a integral. So those limits can include things like the endpoints on your integral, or maybe some point in the middle of your integral, or I should say your interval, in which case you just kind of split it up into two, and you see where the limit will take you, all right? So these are all the different types of improper integrals. Let's maybe do some examples. Yeah.
What is the discontinuous in A and B?
Oh, that's a great question. Then you would just split it up in the middle, and then assuming that let's just kind of draw a picture to see what it looks like. Okay, so let's say that we've got some kind of function that maybe looks like this, and we have like an asymptote on either side. Okay, so but it's defined everywhere else. It's totally continuous. It's all good, but then all of a sudden, on each of our endpoints, it's undefined or discontinuous or what have you. That's fine. Really what we would do is we would just sort of split it up. It doesn't matter where, but yeah, you could just kind of split it up, let's say right here. And then all of a sudden you would have one integral that has just a single bad endpoint. So I guess this would be, type B, 2b. And then the other one over here, this one here, it would be kind of just the opposite. So that's a great question. So it's kind of like the opposite of this type C, right? So you might, like you could spend all day sort of splitting up every single possible case. I mean, you could also have kind of a type 1 and a type 2, right? You could have something that looks like this. You could have sort of like a vertical asymptote, right? Like right there, and then it goes on and on and on forever in this direction too, right? You could think about something like that. In which case, again, really what it would boil down to is like right here you'd have a type 1 that goes off to infinity, so that you have an infinite domain, and then here you have a finite domain, but a point of discontinuity that you'd have to deal with. So there's all sorts of mixing and matching that you might have to do. But the idea is just that you would just sort of chop it off and then deal with whatever interval you have. Yeah. Okay, let's do an example of a type 1 discontinuity. Let's see here. Okay. Thanks. Okay, so here's the integral that we're looking for, right? It's the area underneath this curve. So you can kind of imagine that as you get further enough, you're basically adding nothing, right? So let's see where this takes us. So I'm sure you could probably do this one on your own. It's not too bad. So what we're going to do is we're going to set this as the limit as t approaches infinity of the integral from 1 to t of 1 over x dx, okay? And this, of course, is, it's going to be the limit as t approaches infinity of, the ln of, the ln of x, right? But we're going, in this case, from 1 to t. Okay?
Absolute value of x, no.
Yes, thank you. Absolute value of x. Okay, so this is equal to the limit as t goes to infinity of, we've got the ln of the absolute value of t minus the ln of the absolute value of 1. Okay. And okay, so the limit as t goes to infinity of ln of absolute value of t. The ln of 1 is 0, so we're just left with this. And looks like this is equal to infinity.
How do you calculate that?
Well, it's one of those functions that we kind of just have to be familiar with. So let's take a look at what happens with ln of t. So ln of t, or ln of x rather. Okay. So yeah, it doesn't look like it increases very quickly, but it does. So ln of x is basically like the inverse of e to the x, right? And e to the x, like it grows really, really quickly, right? Like by the time you get to like, 20, it's like way, way up here. Like you can't even really write that number down, right? Let alone like if you get to 100 or 1,000, right? But you can imagine you can still take e to the x, right, for any value of x. So similarly, the same is true for ln. Ln can take on any value. We don't necessarily know what that value is going to be, but it's going to be really big. So yeah, absolutely. The limit as the ln of t goes to infinity is infinity. So yeah, it's kind of weird because this, like the integral of 1 over x, 1 over x, it doesn't look like there's a whole lot going on over here, right? It looks like it's a pretty small amount of area, especially as you get over here. But indeed, it is infinity. So we just have to take their word for it. That's how the cookie crumbles, I suppose. Let's try another one. Let's do a similar one. Let's do 1 over x squared. So we'll do pretty much the same one, except we'll throw an exponent of 2 on that x. Okay? So I've got, okay, let's evaluate and let's do the same interval. So from 1 to infinity of 1 over x squared dx. Let's see what happens. So this is going to be equal to the limit as t goes to infinity of 1 to t of 1 over x squared dx. Okay. Well, this is equal to the limit as t goes to infinity of, the integral of 1 over x squared. So we've got x to the negative 2. So I decrease that by 1, right? And no, sorry, I'm tired. My brain is just not working. Negative x to the negative 1. Yes, you're right. Absolutely. Negative x to the negative 1. Negative x to the negative 1. Thank you. And that's going from 1 to t. Okay. Oh, yeah, and we're going to close those brackets like that. Okay, so this is, we're just going to take the limit after we evaluate this. So this is going to be the limit as t goes to infinity of negative t to the negative 1 minus negative 1 to the power of negative 1. Okay. Look at that, I've got 2 minus signs. Okay, so I've got the limit as t goes to infinity. Let's just write this as a nice little negative 1 over t minus 1. Sorry, this should be minus negative 1, right? So this is actually a plus, right? Because the antiderivative is negative, like basically negative 1 over x, and you subtract 1 from the other, right? So I'm subtracting a negative. So this is like you can think of it like this as negative or minus negative that,
Yeah, so it's
right?
plus.
So it's plus. Okay. So that makes a little more sense. Okay, and then you can see that as t goes to infinity, this goes to 0. So I'm left with 1. So let's see what happens in Desmos here. Just want to take a look at these two graphs. They're going to look pretty similar, I have to say. So I've got 1 over x and then 1 over x squared. Okay, and we're starting at this point 1. So it is quite a bit smaller, but as you proceed, they get quite close. But it looks like the 1 over x squared is almost hugging the x-axis there. So you can kind of see that, yeah, we're getting really small really quickly. So hopefully that kind of paints a picture a little bit. But the gist of it is that we just take the limit and see where the limit takes us. So let's evaluate the definite integral from 2 to 5. 2 to 5 of 1 over square root of x minus 2 dx. Okay. So on first glance, this kind of looks like an innocent question, but this is going to require us to use the fundamental theorem of calculus, which states that the integrand, like the function that we're integrating, is continuous on that interval. And it's not in this case, right? We have a discontinuity when x is equal to 2, and that's in our interval. It's one of the endpoints of the interval, but it's still on our interval. So we do have to approach this with a little bit of care. So let's see what happens. So I'm going to say that this is equal to, so I'll just start again from scratch. So I'll just start off by writing the integral again. I'll write the integral from 2 to 5 of 1 over the square root of x minus 2 dx. That's equal to the limit. And let's use t. I kind of like using t. And really the problem is with this 2. So we're going to have to approach the 2, and we're going to be coming at it from the right. Right, so we've got our function here. Who knows what it looks like? Maybe it looks something like this. And we're going from 2 to 5. Our problem is at 2. So we're going to be approaching 2 from the right. Okay, so I'm going to take the limit as t approaches 2 from the right. And I'm taking the integral of t to 5 of 1 over the square root of x minus 2 dx. Okay. So I don't know about you, but my brain is working at about 30% capacity, so I'm going to just do a substitution, because I feel like if I just go straight to the answer, I'm going to make a mistake. So I'm going to set u equal to x minus 2, and then du is going to be well, just dx. So probably didn't even have to do that substitution, but I want to make sure that I don't mess this up. If you want to just go straight to the answer, you can, but not really filling up for it. So we got that integral. I'm still going from t to 5. I'm going to say that this is 1 over the square root of u du. And this is equal to, let's actually change this to u to the power of negative 1/2. Okay, so I'm going to raise that to a power and then multiply by the reciprocal. So this is equal to 2 times u to the 1/2. And
Oh, I know.
I think that's right.
Yeah.
Limit as t approaches 2 from the right. And this is equal to, oh, and then we're going from 5, or t to 5. And now I'm going to turn this back into x's. So this is equal to the limit as t approaches 2 from the right of 2 times, well, let's actually turn this back into square root 2 times the square root of x minus 2. That looks good. and we're going from t to 5. Okay, we're going somewhere. We're getting there. Okay, so this is equal to the limit as t goes to 2 from the right, and let's just plug these numbers in. So now I've got 2 times the square root of t minus 2 minus 2 times the square root of 5 minus 2. Okay? Well, when t goes to 0,
Can it be the other way?
Why it's
yes, thank you. Let's just do this. Cha-cha-cha. Come on. Oh, there we go. And so 5 should go here. T should go there. Thank you, Nick. Thank you. So when t is equal to 2, well, keep in mind that we're approaching t. T is approaching 2 from the right. If we were going from the left, then we would get a number smaller than 2. In which case, taking the square root would give us a complex number, right? We would not have anything real. So it's okay that t is actually going straight to 0 there, or 2 there, because we're approaching it from the right. So this is approaching 0. Okay, so all this portion here is going to 0. So we can kind of think of this as nothing, and then we're left with 2 times the square root of 5 minus 2 is 3.